Hey, welcome back to another episode in Practical Electronics and Circuits 101. In this series, I explain the fundamentals of circuits with a focus on using this knowledge for practical applications and projects. The link to the full playlist is in the video description in case you want to get caught up with the previous videos. In my last video, I covered inductors, so for today, I figured I'd continue on with the topic of coils and do an introduction to transformers. So let's get straight into it. Now, chances are, everyone watching this has encountered a transformer before, whether you realized it or not. Large transformers can be found pretty frequently in public areas. Sometimes they're hanging up on a power pole, while larger transformers are located on the floor. Most of your electronics devices at home will also have at least one small transformer in them, including chargers for your phone and laptop. Transformers are commonly used in power delivery applications for stepping up and stepping down voltages, but they're also used for a few other applications as well, including some truly interesting devices such as Tesla coils. But let's first discuss what transformers are, and then I'll go into more detail on how they're used. Now, in simple terms, a transformer is just two coils that don't directly touch each other, but they can transfer energy to each other through a phenomenon called electromagnetic induction. I gave an introduction to this concept in my last video when I talked about inductors. But in a nutshell, when electrical current flows through a wire, it also radiates a magnetic field around the wire. Likewise, if a magnetic field is applied to a wire or circuit, it will create a small current in the circuit. But coils produce a unique magnetic field with unique properties. Both transformers and inductors are coils, which take advantage of these properties, but they're not used in the same way. Inductors are used for the way they interact with signals that pass through them when placed in a circuit. For example, in tuned or resonant circuits. But transformers, on the other hand, take advantage of electromagnetic induction in order to transfer energy from one coil into another coil. The original signal goes through the first coil, which is referred to as the primary, and transfers this energy into the second coil, which is referred to as the secondary. Only AC signals will be passed through a transformer, and DC signals will be blocked. For power applications, these coils typically have an iron core running through them to help maximize the transfer of energy. But it's interesting to note that this iron core isn't necessary. In other words, the two coils don't need to have any physical contact with each other in order for them to transfer energy. But like I said, for power applications, the two coils are connected to each other with an iron core through the middle of them to maximize this transfer. Additionally, the efficiency and effectiveness is also determined by the amount of inductance in the two coils. The inductance value of a coil can be found with this equation here, where L stands for inductance. The symbol mu stands for permeability, and this value will depend on the material used. For example, pure copper will have a certain permeability, while an alloy will have a different value. The letter N stands for the number of turns in the coil. A stands for the area, or more specifically, the coil's cross-sectional area. And finally, the lowercase l stands for the length of the coil. This equation is something I probably should have shown in the last video since it's directly related to inductors, but here it is. This equation also directly applies to transformers as well. The size of the coils and the number of turns they have need to be considered when designing transformers. The number of turns in a coil not only plays a role in the inductance, but also determines how much the voltage will be stepped up or stepped down, which is the first application I'll be going over today. The ratio of the number of turns in the primary coil over the secondary coil equals the ratio of their respective voltages. So if the primary coil has 5 times as many turns as the secondary, then the secondary's voltage will be the primary's voltage divided by 5. Let's demonstrate this with a straightforward example. Here's a schematic of a simple 5-volt DC power supply. And this is actually the same one I showed in the last video where I explained the purpose of these decoupling capacitors. But this time let's focus on the transformer. Let's say this transformer's primary winding has 1000 turns, while the secondary has 100. This will give a ratio of 10 to 1. So if the primary is connected directly to a standard power outlet which provides 120 volt AC power, then this will be stepped down to about 12 volts AC in the secondary coil. This 12 volt AC signal is then connected to what's called a full bridge rectifier, which is just 4 diodes arranged like you see here. The full bridge rectifier is what converts the AC voltage into a DC voltage, but I'll be covering diodes in my next video, so stay tuned for that. Now, some transformers also have what's called a center tap in one or more of the coils, which allows you to essentially split that coil in half. So if the secondary in this example had a center tap and we measured the voltage across one of the outer legs to the center tap leg, then we would get 6 volts AC. This way we now have access to both 12 volts and 6 volt power from a single transformer, which saves cost and space as opposed to using 2 separate transformers to extract these voltages. Whether you need a center tap transformer or not, all depends on if the device you're powering could use that additional voltage or not. This simple 5 volt power supply has no use for a center tap, so it would be pointless to use a transformer that had one in this example. Now, something to keep in mind is the total power that the transformer can deliver can't exceed the total power that the source can deliver. To illustrate this, let's now look at a step-up transformer instead of a step-down transformer. Let's say this time, the primary has 100 turns and our secondary has 1000 turns. This gives us a 1 to 10 ratio, meaning our secondary will output a voltage 10 times higher than our primary. So if we connected this to a standard 120 volt outlet, then we would be boosting this up to 1200 volts in our secondary. However, just because it's boosting the voltage doesn't mean we're boosting the power it can deliver. The current must also scale along as well. So if our 120 volt outlet can deliver, let's say 10 amps, then that means the 1200 volts coming out of the secondary will only be able to deliver 1 amp. 10 times as much voltage means we have 10 times less current at our disposal. Every transformer will also have a maximum power rating that they can handle. Larger transformers typically use thicker wire gauge and can handle higher currents than smaller ones can. Also, keep in mind that transformers aren't 100% efficient, but they're surprisingly close. Most transformers will have a full load efficiency of at least 95%, which is incredibly efficient. But it's not perfect, so you'll lose a little bit of power in the process. This is why large transformers can get pretty hot and need radiators to cool them down. Now, transformers have a few other uses as well, including impedance matching, DC isolation, and interfacing between balanced and unbalanced circuits, which are useful in several applications, especially audio applications. For example, a guitar amplifier will typically have 2 transformers. A power transformer for stepping up the 120 volt AC power into higher voltage for the power tubes, and it will also have an output transformer to step down the high voltage signal coming from the power tubes down to a low voltage high current signal for the speakers. But not only do transformers change the voltage and current, but they also change the signal's impedance. The output transformer is changing the power tube's output from a high impedance output into a low impedance signal that can effectively drive the speakers. Impedance is very similar to resistance, except impedance tells us how alternating current is affected by the resistance rather than direct current. Impedance is determined not just by the ohmic resistance, but also by the reactance of a circuit. Impedance matching is important for making sure power is efficiently delivered to the load, and also has a big impact on the frequency response as well. If the impedance of the signals going in and out of audio equipment isn't matched well with each other, then your audio might sound weird and certain frequencies might be drowned out. If you take a look at the specs for various audio transformers, you'll notice their winding ratio is given in ohms. That's because the exact voltage doesn't matter so much in these applications, but rather their purpose is to modify the signal's impedance and also to provide DC isolation. If you're a guitar player and have ever tried to connect the output of your computer's audio interface directly into a guitar amplifier, then you probably notice the results are pretty bad. This is because of two reasons. For one, the audio interface is outputting a line level output, whereas the amplifier is expecting an instrument level signal. This is an example of impedance mismatching. Another issue is digital noise caused by ground loops, which is quite common when you try to combine computers and professional audio. A coupling capacitor will not help here, and the best solution is to use what's called a reamp box, which is actually just a small audio transformer. Since transformers contain two coils that aren't directly connected to each other, this provides true isolation between the circuits and components that are connected to it. To be specific, this is known as galvanic isolation. Now there's one more application I wanted to briefly touch on. If you're into sci-fi and fantastical technology, then you've likely heard of Nikola Tesla and some of his wondrous inventions such as the Tesla Coil and the prospect of wireless power. And while these topics certainly aren't practical for beginners' projects, I think Tesla's inventions are incredibly interesting, so I thought it would be fun to spend at least a few minutes talking about them since they're relevant to today's topic. The Tesla coil is classified as a resonant transformer circuit, and they contain a transformer that steps up the voltage to ridiculously high voltages. Smaller Tesla coils can produce voltages up to several 100,000 volts, while large Tesla coils can get up to millions of volts. Such high voltages produce what's called electrical arcing. Normally, when electricity flows from one conductive point to another, it requires a wire to flow through, obviously. But at extremely high voltages such as these, the current is actually able to travel directly through the air. Now, you might think it would be dangerous to be near a device that's releasing millions of volts into the air. But keep in mind this is a high voltage, low current AC signal. Hardly any current is being transferred, relatively speaking. But the other reason is that Tesla coils are a resonant circuit operating at a very high frequency. If you recall from my previous video, I talked about LC circuits, also known as resonant circuits. While the Tesla coil is a high voltage example of an LC circuit operating at a high frequency, as we can see from this simple schematic here, the capacitor value is chosen to create high-frequency oscillations that are typically between 50 kHz and 1 MHz. High frequencies have an effect where the current will travel around your skin rather than penetrating your body, which means you won't be killed by a Tesla coil, but you don't want to get too close as it can still cause severe burns. And while Tesla coils produce a magnificent display of electricity that looks similar to lightning bolts, this isn't how Tesla coils power things, such as these light bulbs here, but rather its magnetic field is what powers devices from a distance which can't be seen by the human eye. But interestingly enough, large Tesla coils aren't very common these days, and are mainly used for entertainment purposes rather than what Tesla intended them for, which was apparently for long-distance wireless power. This concept has traditionally been treated as a tinfoil hat conspiracy theory by the mainstream, but wireless power not only is a possibility, but it's already a reality, at least for short distances. There are phones on the market today that can be charged without any wires, and instead use what's called inductive charging. Now, to be clear, these aren't examples of Tesla coils. The charger and phone need to be right next to each other in order to work, and they operate more similar to a standard transformer than a Tesla coil. But it just goes to show that the concept of wireless power using electromagnetic induction is definitely real. But using Tesla coils for long-range power transmission seems to have a few issues. Most notably, its strong EMF can interfere with nearby devices and in some cases can even damage some devices. Also, it appears that not very much current can be transferred in this manner, which means its capabilities would be pretty limited. But I'm not exactly an expert on this subject, and who knows exactly what Tesla had in mind, since all of his work was confiscated by the government when he died. Tesla coils definitely aren't a practical project to start out with, but I think they're really cool, and I'd personally like to learn more about them myself. So at some point in the future, I think I'll probably be coming back to Tesla coils, and will be making some videos on my experiments with them. But I probably won't get into this until at least a year from now. So until then, I have some other fun projects planned that are more geared for beginners. But anyway, that wraps up today's lesson. If you found this video to be interesting, then be sure to give it a thumbs up, and also consider subscribing to the channel if you haven't already. Also, feel free to ask any questions or just let me know your thoughts in the comments section. As always, thanks for watching, and I'll see you in the next one.